See, in the last class, we have already studied about the errors, the absolute errors, the relative errors, how do we compute those errors. In this class, we will study how do those errors propagate when we are doing computation on quantities which have errors. So there is a simple example. Let's say that we are calculating the value of momentum denoted by the symbol P using the formula m into v. We have calculated, we have measured the value of m with certain amount of error. We have measured the value of v with certain amount of error. Now we want to understand, in this class we will understand how do those errors propagate when we multiply two quantities which have error. So we will find out what would be the error in P given the errors in M and V. So that is the objective of this class. See, the errors propagate differently in the case of when we are doing sums and differences and when we are doing products and divisions. So the errors propagate differently. In the case of sums and differences, if I have a computed quantity Z, which is given as sums of all the A's, which is A1 plus A2 plus AN, and difference, okay, of all the B's, which is it is the Z is equal to A1 plus A2 AN minus B1 minus B2 minus BN. Then the final error in the computation of Z, the absolute error, okay, note that this is the absolute error. Delta Z means that it is the absolute error in Z. Similarly, delta A1, delta A2, this delta denotes the error in the corresponding quantity. So the final absolute error in Z would be the sum of errors in all the A's, delta A1 plus delta A2 plus delta AN, plus, note that this is a plus sign. Although in the formula for the actual Z we had minus, but here we are not using the minus. It is plus sign plus all the errors in all the B1s. So no matter whether the quantity is calculated using sum or difference, no matter of whether it is sum or difference, the absolute error is always going to be added in the computation of the error of the final quantity. Okay, so we'll understand this formula using an example. Okay, that would make these things very, very clear. So let's say that we have two resistances in parallel. Okay, so very, very simple example. R1 and there is a second resistance, sorry, these are in series. Okay, there is a second resistance R2 and these two resistances are connected in series. So here, let's say the value of R1 is 200 and we have measured it. So there is a certain amount of error in this measurement, and this error is plus minus 4. Okay, and of course the unit here is ohm. Okay, so we'll just write the unit. Always in physics we'll take the units with us. And R2, similarly we have computed it to be, we have measured it to be 100 plus minus 3 ohm. Now we know that when resistances are connected in series, what is the final value of the resistance? The final value of resistance is simply the sum of these two resistances. So final value of resistance is R is equal to R1 plus R2. Now we are interested in, given the error in our measurement, we are interested in finding out, let's first find out what is the maximum possible value of R that we can have. So maximum possible value of R will happen when we have maximum value of R1 and when we have maximum value of R2. That is 200 plus 4 and we'll add it with 100 plus 3. Okay. So what is the maximum value, possible value of this R? This comes out to be, first we'll add 200 plus 100, that comes out to be 300, and then there is a plus 7 here. So that is the maximum value of R, will denoted by R max. Okay. And what about the minimum value of R? Let's just say that it is R min. Minimum value of R will happen when we choose the minimum value of R1, which is 200 minus 4, and we will add it to the minimum value of R2, which is 100 minus 3, and this comes out to be 300 minus 7. So I can combine these two and I can write the value of R given the range, I'll give it as a range now, will be 300, and the maximum that I have to add is plus 7, and the minimum I can subtract, the maximum I can subtract the range of, to get the range of R is minus 7. Okay, so if you notice what has happened here is that we have the 7 has come from the absolute value of R1 plus absolute value of R3. Okay, so the absolute errors just get added in the case of computation of R. The absolute value of R1 and R2 just get added. Now, for some reason, let's say that now you have to calculate R1 minus R2. In this case, what would happen? Let us understand that also in the case of subtraction also we are saying that the absolute value errors would get added. Now, let's see why that happens. So, in the case of subtraction, what would happen? We are doing R1 minus R2. Again, we will compute the maximum value of R. So, okay. So, maximum value of R is again R max. Okay. And R max will be R1 minus R2. R1 minus R2. So, what is the maximum value of R max? It will be maximum when R1 is maximum and R2, since it's getting subtracted, R2 is minimum. That would be the maximum value of R max. So R1 becomes 200 plus 4 and R2 becomes, we'll take the minimum value of R2, which is 100 minus 3. So if you notice, because of this subtraction sign, although 200 and 100 will get subtracted, so I'll get a value of 100, this plus 4 and this minus 3 will actually get added. So even in the case of subtraction, my maximum value comes out to be 100 plus 7. That is, the error is still remains 7 only. Okay. Similarly, the minimum value of R min, I leave it as an exercise for you, but if you compute it, that will come out to be 100 minus 7. Or the range of R again comes out to be 100 plus minus 7. That is, the error, the absolute error is always getting added, no matter whether we are using subtraction or we are using addition in the case of R. Okay. So this is the case of sums and differences. In the case of sums and differences, the absolute values get added. What happens in the case of products and quotients? So let's say that there is a quantity we are computing, which is computed using the products of all the A1s, okay, which is right here at the top, divided by all the B's. Okay, so it is the product of all the A's divided by all the B's. That is the value of Z. In that case, the relative error in Z, okay, this is the relative error. We have already studied in our last class. Delta Z, which is the absolute error of Z divided by Z itself, gives me the relative error in Z. So relative error, okay, so this is the relative error in Z is equal to the sums of all the relative errors in A's plus, again, note, although B's appear here in the division, but here we are adding all the relative errors of B's as well. Okay, so what is the final relative error in the computation of Z? It is the sum of relative errors of everything in the numerator plus sum of relative errors with everything in the denominator. Whether the quantities come on top, numerator, or at bottom, does not matter. We always add all those relative errors in all those quantities to get our final error. So let us understand why this happens. In the case of sums and differences, things are pretty obvious, but here that might not be the case. Let us just look at the momentum example itself. Okay, so we know that momentum P, and we will just write it as P plus delta P because we are interested in error. So we will have to write our error here. That is equal to M plus delta M. Delta M is our error. Okay, and we'll just use the plus minus sign. Both signs will use plus minus. Okay, so that is my measured quantity of M, which comes with an absolute error of delta M multiplied by velocity V plus minus delta V. So error in V is given by, absolute error in V is given by delta V. So that is my formula for momentum in the case of M and V if they have absolute error of delta M and delta V. Let us see what would be the maximum value of this momentum. See, the maximum value of this momentum is of course P plus delta P, and this maximum value of momentum would come when both M and V have their maximum value. That is understood, right? When the two quantities in products have their maximum value, then only the final product has the maximum value. We understand that. So this maximum value will come when I choose M plus delta M multiplied by V plus delta V. So that is the maximum value of my momentum. And if I compute this comes out to be this M and V will become MV. So this is M and V multiplied. Now this M and delta V will get multiplied and I'll get another term here, which is plus m delta V, and then I'll get another term delta m into V, which I'll write it as delta m dot V, plus there will be another term which is delta m into delta V. So there will be a fourth term here. I will not write it. Why? Because see, the errors are so very small. We are assuming that delta m and delta V are so small that their product delta m into delta V will be very, very small, and we'll just ignore it. We will just not write it at all. Okay, so there will be a product here which I'll denote by a symbol epsilon, but that is so very small that we are just ignoring it completely. It's delta m into delta V. We are just ignoring it completely. So now, in the case of P plus delta P, what happens? This comes out to be MV. MV is again just will divide MV and P are the same. Okay, so P is equal to MV. That is my basic value. Okay, so I'll always remember that the basic value we simply compute. We don't take into account the errors. We just calculate the measured quantity and we multiply it. That is our basic value. So actually P and MV are the same. So the right hand side, I will divide the entire right hand side by MV. So I'll just write it as such, delta V plus delta M dot V, and this entire right hand side I am dividing by MV, and the entire left hand side I will divide by P. But that is okay. I am dividing by two different quantities, but P and MV are equal, so I can essentially divide this side by P and this side by MV, but that is okay, right? Because we understand that P and MV are the same thing, so I can divide that. I can do division this way. So this P and P, okay, so if I now separate out P, I can write it this as 1 plus delta P by P. So I am separating out the denominator. That's what I am doing here. This MV and MV, this becomes 1 plus, notice the plus sign here. This M and M would cancel when I separate out the denominator. So this comes out to be delta V by V plus this V becomes V. This V and V would cancel, sorry. This V and this V would cancel. So this becomes delta M by M. Okay. So finally, if I look at this very, very closely, what do I find? I find that my delta P by P, which is my relative error, okay, delta P by P, that is my relative error, actually comes out to be delta V by V plus delta M by M. Okay, so this is what we were trying to say. We were saying that the relative error in P, which is delta P by P, is actually equal to the sum of relative errors of the two individual quantities which I am trying to multiply, which is delta V by V plus delta M by M. So this is the relative errors are actually getting added in this case. The same thing would happen if we try to compute P minus delta P. Again, let's just do it a little bit. I'll just give you an intuition for why that would happen. The minimum value of P, that is P minus delta P, is the minimum value of P. That would happen when we take the minimum value of M, which is M minus delta M, and we multiply it with minimum value of V, which is V minus delta V. Again, we will get a term here which is MV. We will get a term here which is delta M into delta V, which we'll just ignore because delta M to delta V is very, very small. But here I will get a term which is very similar, which will look like delta M into V plus M into delta V. So that term will come here. And here again I have a minus sign, and here again I have a minus sign. So if you look at delta P, if you divide the entire thing, both the sides, here I'll divide by P, and here again I will divide by MV. I'll do this division, and this will come out to be 1 minus delta P by P will be equal to 1 minus delta M by M plus delta V by V. So if you notice, again the delta P by P, the maximum value of error as well as the minimum value of the relative error in the case of P, always comes out to be, or the relative error in the measurement of P always comes out to be the sum of the relative errors of m and some of the v. So that is the formula. That is the formula that we derived for two quantities. We can generalize this for n number of quantities, and in each case our higher order terms would just cancel out, and in each case we will be left with the single formula which we have discussed here, that the relative error in the final measurement is equal to sum of relative errors of all the products plus the relative errors of everything in the denominator. So now we have seen that the relative errors in the products, how do they propagate, right? We know that, we understand that they propagate as the sum of the relative errors. But here in this formula we are saying that the relative errors in the case of when something is in the denominator, even in that case the relative errors propagate as sum of those quantities which are in the denominator. Let us understand this second part as well, okay, so that our entire thing is fully we understand it. So let's say that we have a simpler z which is computed as the division of a and b. So it is a by b, very simple. So now we are trying to find z plus delta z when we have measured the quantities a as a plus delta a divided by b plus delta b, okay, and we are trying to find out what would be the value of delta z in terms of delta a and delta b. So how would we compute that? See, the problem comes because the b is in the denominator. So we will use a very special technique which is known as binomial theorem to solve this problem, okay. So in the case of, we'll use the thing called binomial theorem, but before we do that, let us first understand what would be the maximum value of z. So the maximum value of z, okay, this is plus minus, this should be all plus minus because we are interested in the entire range of z, okay, in terms of the entire range of a and entire range of b. But first we'll focus on the positive value of delta z, which is the maximum value of z. This maximum value of z will be given when I have taken the maximum value of the quantity in the numerator, which is a plus delta a, and the minimum value of the quantity in the denominator, because there is a division there. So I have to take the minimum value of b. So minimum value of b will be equal to b minus delta b, okay. Now remember that this b is delta b is the error in b. This delta b we are assuming all the time is very small. So because this delta b is so small as compared to b, what I'll do is that first I'll write this as a by b 1 plus delta a by a divided by 1 minus delta b by b, okay. So this delta b by b is very small, and so I can use binomial theorem here, and the binomial theorem tells me that 1 divided by 1 minus delta b by b is actually nothing but this. First I'll write this one, delta a by a, and this 1 minus delta b by b I can write it as 1 plus delta b by b, and there will be additional terms here, but because delta b is very small, that quantity 1 minus delta b by b, because of binomial theorem, okay, so here to here we went because of binomial theorem, and there will be additional terms in the expansion of 1 minus delta b by b, but I can ignore those because delta b by b is very small. And again, using this binomial theorem, even in the case of when b is in the denominator, my value of z plus delta z, the maximum value of z, comes out to be the quantity which is same as when the b would have been in the numerator. So the maximum value of z again comes out to be very similar to as would have been as if the b was in numerator itself. So it is 1 plus delta a by a multiplied by 1 plus delta b by b only. Okay, so even in this case I can say I will divide this entire thing by z, and this comes out to be 1 plus delta z by z is equal to, I'll divide this entire thing by A by B, because that is what Z is, A by B, and this comes out to be 1 plus delta A by A. This A by B would get cancelled because I am dividing this entire thing by A by B. This entire thing I divided by Z, and this entire thing I have to divide by A divided by B, because that is what Z is ultimately. Z is A by B. Okay, and this comes out to be 1 plus delta B by B. If you expand this, the multiplication of delta A by A and delta B by B, this term would cancel because this is again very small. So this comes out to be 1 plus delta Z by Z is equal to 1, and then plus delta A by A plus delta B by B. Okay. So this 1 and multiplied together will give me 1. This 1 multiplied by delta B by B would give me this term. This 1 multiplied by delta A by A would give me this term, and the fourth term, delta A by A multiplied by delta B by B, we will again ignore because that would be very small. So if you notice closely, delta Z by Z, which is the relative error in Z, comes out to be again the sum of the relative errors of A and B, even when A is divided by B. Similarly, we can also prove that 1 minus delta Z by Z would come out to be 1 minus delta A by B, delta A by A plus delta B by B. So there will be a common minus there. Okay, so we can similarly prove that plus delta B by B. Okay, so there will be a common minus here. Ultimately, this delta Z by Z comes out to be this quantity only. Okay, so with this we have proven the errors in the case of products and quotients also. Now let's take a numerical and try to solve it. So here what we have seen is that there is a formula for length in the case of surveying, which is a combination of 3 lengths, which is given by a combination of 3 lengths. The length L is given by L1 multiplied by L2 divided by L3. We have seen that in the case of multiplication and division, we do not work with absolute errors. We only work with relative errors. Our error in terms of L1 is given as an absolute error. L2 also, in all the 3 cases, the errors are given as absolute errors. The very first step we will need to take, we will have to convert these absolute errors to relative errors before we do anything else, because we are dealing with products and quotients here. So the absolute error in L1, delta L1 by L, will be equal to 2 divided by 200 into 100. We'll just use percentages so that things become simple. This comes out to be 1%. Similarly, if we compute the error in L2, the relative error in L2, which is delta L2 by L2, okay, in percentage, this will come out to be 2%, and our delta L3 by L3 would come out to be 4%. Okay, so again we have used some approximations here, but that is what ultimately it is: 1%, 2% and 4%. You can compute it yourself. What would be the final value of error, final relative error in L, which is delta L by L? We know that in the case of products and quotients, the relative errors just get added. So we will just add, that will be nothing but delta L1 by L plus delta L2 by L plus delta L3 by L. And of course, this comes out to be 1% plus 2 plus percent plus 4%. This comes out to be 7%. What is the value of L? The value of L, okay, this is the quantity, the value of L itself without any error. So when we compute the value of L itself, we are not using any kinds of errors. The value of L, if I compute it, this comes out to be L is equal to L1 into L2. L1 is 200 into L2, which is 5.5, divided by L3, which is 10. Okay, if I compute this, this comes out to be 110. Okay, so my delta L by L I know is 7%, L I know is 110 feet. So what would be the absolute error? Absolute error delta L will be equal to 7% of 110. Very simple, right? That we have just computed from this relative error, we have to convert back to the absolute error in L. Okay, so first we individual quantities, we computed their relative errors, we added those relative errors to get the relative error in L. Now we have to go back from that relative error in L to absolute error in L. So I have to compute what is the delta L, the absolute error in L, that is 7% of 110. That roughly, if you compute it, this comes out to be 8 feet. Okay, it will be 7.7 feet, but we'll round it off to 8. See, why we are computing everything only, we are not putting any decimal points, we are not computing anything after decimal point. Why did we do that? Because one of the values L1 here doesn't have a 200.0. It is only computed, we only know its value to the correctness in the units place. So our computations, everything would only go till units place. If we compute the 1 point after the decimal, that is the 10th place or the 100th place, it makes no sense, because one of the values here, the value of L1, we know only correct till the units place. So that is what our final computation will reflect. Okay, so here now we know the value of delta L, we know the value of L, so we will write the final value as 100 plus minus 8, and the feet will go here common. Okay, so that is the final value. Now the next thing that we will understand is that if I have a quantity z, which is equal to b, which is a constant, b times a, so how would the error in a affect the error in z? Okay, how does this multiplication by the quantity b affect my error? The absolute value of the error in z will be equal to b times the absolute value of error in a. So this is only about absolute error. Actually, the relative error in z will be the same as the relative error in a. The relative error in z will be the same as the relative error in a, but because z is actually b times a, the absolute value of error in z will also becomes b times that of a. So very simple. Okay, and this fact we are mentioning because it is asked in the exam, and the reason is this has very practical purposes. Let's say that I have several papers, I have a bundle of papers right here. Okay, so I have a bundle of papers, but I don't really want to compute, I am not able to accurately measure the thickness of this one of these sheets of paper. I cannot measure that. So what I'll do is that I'll just pile up several sheets of these papers as this person has done here, and then I'll measure the height of this pile. Okay, the value of one sheet will be the height of the pile divided by number of sheets I have, provided that all the sheets measure the same, they have the same thickness. If that is the case, then I can measure the height of the pile and then divide by number of sheets. Let's say I have 100 sheets, I'll divide by 100 to get the thickness of one sheet. But when I'm dividing by 100, I'm not only dividing the thickness of the entire pile to get the value of sheet, I am also dividing the error. My error would also reduce by a factor of 100. That is a very good fact, that when we calculate the thickness of pile and we divide by number of sheets to get the thickness of one sheet, we are also dividing our error I have made in measuring the value of that pile. Okay, so my error will also become 100 times less. So that is the fact which is useful. Now the next important law is uncertainty. How does it propagate when we have the sign, when we have the power, when we are calculating power of something? So for example, there is a quantity z, which is equal to a raised to power n. The relative uncertainty, okay, so this is the case with relative uncertainty. Okay, the relative uncertainty in the computation of z will be equal to n times the relative uncertainty in a. So that is the simple thing, and we know this comes because a raised to power n is nothing but a into a n times. Okay, it is a multiplied n times. So naturally, since I am multiplying a n times, in the final computation of z, the error would be added, the relative error would be added n times. So that is what this formula is reflecting. So the final computation of z, delta z by z, will be equal to delta a by a plus, right, the a is multiplied n times, therefore the error would be added n times, delta a by a n times. And this, if I add n times, is nothing but n multiplied by delta a by a. Okay, very, very simple. So this absolute value of n we are taking because no matter whether n is positive or negative, this formula would hold. Our error would always become n times, because we have already seen that no matter whether the quantities are in numerator or they are in denominator, their relative errors always get added. So no matter whether n is positive or negative, the relative errors would always get added to give me the final error in Z. So we'll take an example of this. So here we have a cube whose side we have measured. Okay, so we can only measure the side. We only have a ruler, for example, and using that ruler we have measured the side to be 2 centimeter, but there is an error there. Okay, the error is how much? We have used some kind of vernier calipers and we have measured it to great accuracy, and the error is actually equal to plus minus 0.02 centimeter. That is my error there. Now I have to find the volume of the cube. Volume of the cube is very, very simple. That is just simply V, the volume, is equal to a raised to power 3. In this case, that will be 2.00 raised to power 3. That will come out to be 8.00. That is my volume. What about the error in the propagation of error? We know that if a is raised to power 3 here, our error, our relative error would actually be multiplied by 3. But first, we have to calculate the relative error in our measurement. So we will find out delta. So let's say that this side we are denoting it by quantity known as A. So we will compute the relative error. Delta A by A will be equal to 0.02 divided by 2 into 100. We'll just use percentages because it makes things a little bit better, and this, if you compute, this comes out to be 1%. What would be the error in measurement? Delta V by V will be equal to, since our n, our power is 3, we'll multiply this relative error in A by 3. So this comes out to be 3 into 1%, or this comes out to be 3%. But of course, this is the relative error. We want to go back from this relative error again to absolute error in V. So now we can say that delta V will be equal to 3% of V. Of course, this V we have already computed it. It was equal to 8, and 3% of 8, you can compute it. It's very simply 8 is a 24. This will come out to be 0.24. Okay, why does it come out to be 0.24? Because this is percentages. So it was 3%, so it will be 3 divided by 100 into 8, which comes out to be 0.24. And we should not forget our units here. This is given in centimeter cube, because that is what 8 is. 8 is in centimeter cube. Okay, this is in centimeter cube. So now what happens to my final value of V? My final value of V comes out to be V plus minus delta V. I write it as 8.00 plus minus 0.24, and of course we should never forget our units, centimeter cube. That is my final answer. Okay, so these things are very, very simple. There are only 4 things that we have to remember: error in propagation of sums, error in sums and differences, error in propagations of in the case of products and divisions, error in propagation when we are multiplying by a fixed quantity, a constant quantity, error in propagation when we are raising the quantity to a measured quantity to a certain power of n. And those are the 4 formulas that we'll have to remember. In the subsequent class, in the next class, we will discuss more numerical problems based on this topic, based on these 4 formulas. And so definitely do watch those classes and solve the numericals yourself, please. Thank you very much.